The algorithms header of the standard library implements a total of 12 different algorithms for searching through a range. Some operate on any range, others only on sorted ranges. Some search for a single element, while others search for a subrange. This one only tells you whether the element exists in the range, while these are great for figuring out where to insert the next element. Today we're going to take a deep dive into all of these algorithms. We'll explain what they do and when to use which one to get the best performance. We'll start with the find family of algorithms, beginning with the standard find. As all the algorithms we'll discuss today, find takes its input range using two iterators. As a third argument, it takes the value to search for. I can, for example, search this container A for the value 4 by passing the begin and end iterators of the container. Find will then do a linear search from begin to end to find the 4. Once it finds it, it will return an iterator to that position. This means that find will always return the position of the first element which matches the search value. If there is no such element, it will return the end iterator. Find has a couple of variations. Find if allows you to specify a predicate instead of a value to search for. Lambdas are an easy way of specifying such a predicate. We can, for example, use a predicate to find the first element that is bigger than 7. Another variation on find is the find if not convenience function. This function does exactly the same as find if, but it inverts the predicate. It can be useful if you already have a predicate lying around and want to use it for both find if and find if not functions. But I must admit that I rarely use this one myself. Find first of is another interesting convenience function. It allows you to search for the first element that matches any of the elements in the search range. The search range is specified using the third and fourth arguments of the function. In this example, we are searching through the whole container A to find the first occurrence of either 4, 6 or 3. Find first of also accepts a binary predicate as an optional fifth argument. This predicate will be used to test for equality. Here we supply a lambda that will consider two integers equal if they differ by at most 1. With this new definition of equality, the number 7 is now identified to be equal to the number 6 from the search set. Of course, find first of could also be written as a find if with a lambda that checks whether the input element is one of the search elements. But in my opinion, using find first of is just a bit simpler and leads to more expressive code. So it's a good one to have in your toolkit. So at this point we've talked about 4 different kinds of find algorithms. They all work on any kind of input range and try to find a single value. Next we'll look at algorithms that search for a specific subrange of consecutive values. Starting with a special one, adjacent find. Adjacent find looks for 2 adjacent elements that are equal. It accepts an input range and an optional predicate to check for equality. Used without such a predicate, it will find the 4s at indices 4 and 5 and returns an iterator to the first element of the adjacent pair. In the second example, we use a differs by 1 predicate to consider an adjacent pair to be equal if they differ by exactly 1. There are 2 such pairs in our input. Adjacent find returns an iterator to the first pair of equal elements. If you're not interested in adjacent elements, but are looking for a specific sequence of elements, you can use standard search instead. Standard search accepts 2 ranges, one to search in and one to search for. It will then return an iterator to the start of the first occurrence of the search range, or the end of the input range if the search range does not occur in it. Note that, in this example, the search range occurs twice in the input range, but only the first occurrence is returned. This allows you to find all occurrences of the search range by repeatedly calling search using the iterator returned by the previous search plus 1 as the begin iterator for the next search. Just like with previous algorithms, you can again supply a custom comparison function if you want to use a different definition of equality, or the types stored in your range don't have an equality operator defined. If you only want to find the last occurrence of your search range, you can use the findEnd convenience function. FindEnd follows the same convention as search. The first 2 parameters specify the input range, the third and fourth specify the search range. FindEnd will return an iterator to the start of the last occurrence of the search range in your input range. Now that we are on the topic of search algorithms anyways, searchEnd can be used to look for a given number of consecutive occurrences of a certain value. In this case, we are looking for 3 consecutive occurrences of the number 4. And with that, we have now discussed all the algorithms that work on any input range. Looking at the overview, we see that we have exactly 4 algorithms to look for a single value and 4 to search for a sequence of values. While these algorithms can be used on any input range, There are some specialty algorithms that will give you better performance if your input range is sorted. But before we have a look at them, I should first talk about the difference between equality and equivalence. The search algorithms that operate on unsorted ranges look for elements that are equal. At the same time, the search algorithms that operate on sorted ranges only use the less than operator when trying to find the elements you are searching for. And as a result, they can only find elements that are equivalent to the element you are searching for. An element A is equivalent to an element B if A is neither smaller than B nor B is smaller than A. For most cases, equality and equivalence boil down to the same thing. But if you use a custom less than comparator, you might find that you end up in a situation where this is not the case. We'll share an example in a bit. First, we go to the most famous kind of search algorithm, binary search. In contrast to previous algorithms, binary search only returns a Boolean value to indicate whether the search value, 3 in this case, exists in the range, or to be more precise, whether there's an element that's equivalent to 3. Optionally, you can supply a comparison operator as the fourth argument. This should of course be a less than operation, as binary search uses equivalence, not equality. Here I'm passing a lambda to compare instances of a point class based only on their x-coordinate. In this example, binary search will return true, as the third element, though not equal to the search value, is equivalent to it, since the less than operation only considers the x value. Of course, often you don't want to find out whether an element is in a range, but you actually want to know where to find it, so you can update it or perhaps remove it. This is where equal range comes in. Equal range has a somewhat misleading name, as it returns a pair of iterators to the range of equivalent elements. When using equal range with the default less than operator, there is no difference. But again, if I use a custom less than, such as this lambda, the distinction becomes important. Here we define A to be smaller than B only if A is smaller than B and the difference between A and B is more than 1. Looking at the definition of equivalent, we find that 2, 3 and 4 are all equivalent to our search value of 3. The last two algorithms on sorted ranges are lower bound and upper bound. They return the start and end iterator of a call to equal range. In other words, lower bound returns an iterator to the first element that is not less than the search value, while upper bound returns an iterator to the first element that is greater than the search value. These algorithms are useful if you want to find the spot to insert a value either just before or just after the equivalent range. Just be aware that you can simply compare the iterator returned by lower bound to the end iterator of the container to check whether an element exists. For example, here we have a call to lower bound using a default comparator, searching for a value that does not exist, the value 6. As you can see, the iterator returned by lower bound is indeed the first value not less than 6, which is different from the end iterator. And with that, we can now make our final overview of search algorithms. I hope this helps you to find the right algorithm to search through your ranges. Of course, if you want to search through a container that supplies its own search operations, such as the standard string or map, you might find better algorithms there. We'll dive into the container-specific algorithms in the next video. Leave a like and subscribe if you enjoyed the video. Thanks for watching.